Good afternoon, everyone. Welcome to the North Carolina Museum of Natural Sciences. My name is Chris, and I am your host today for our Lunchtime Discovery Series here inside the SCCU Daily Planet Theater. Thank you for coming out and joining us. If you can hear the sound of my science-y voice and you think there must be something interesting going on, come on into the Daily Planet, grab a seat on the first, second, or third floors and join us. We've got a special guest presentation this afternoon. Every Wednesday, in fact, here inside the Globe, we bring in experts to share with us a little bit about what they know a lot about, and then we have the opportunity to ask questions of them. And this program every Wednesday at noon is brought to you by us here at the museum, but that's in tandem in collaboration with the Department of Environmental Quality's Office of Environmental Education. So many thanks to them for working with us to put on a great program for you every week. And I'm so thankful that you're all here to hopefully learn something new. How many of you live pretty local to the Raleigh area? Yep. So that means basically every month, if we get rain, you hear about flooding in Raleigh, right? Thinking like Crabtree Creek, but maybe also you might notice like just the little ditches and streams that maybe are around your home or on the side of the roads. I was wondering recently, like driving around and looking at some of these things, what's the difference between a ditch and an urban stream? Could you actually tell just by looking at one? And then you see them, they just sort of duck under a road and they vanish. And you wonder, did somebody build a stream here? Did we just carve out a ditch because we needed some place for water to go? Or was this a natural feature? Was it something that was always been there, and now we're trying to work around it for development and agriculture and all these other land use reasons? Well, there's somebody who thinks about that stuff, and it's Dr. Krissy Hopkins from the U.S. Geological Survey, whose office is right here in Raleigh. Please put your hands together and get ready to learn something new with Dr. Krissy Hopkins.
Thank you. All right. Well, thanks everybody for being here, and thanks folks online. So today we're going to take a little journey through our urban streams in our city here in Raleigh. So I'm going to tell you a little bit about some urban streams here in Raleigh. Just a little bit about myself. I am an urban hydrologist with the U.S. Geological Survey. An urban hydrologist studies how urban development alters the way water moves through a city. So my love for streams started out in this stream in this photo here. This is a stream that ran behind my house when I was a little kid growing up. My sister and I used to run through that culvert. Let's see if I can get this pointer to work. Maybe. Right there. My sister and I used to run through that little culvert that runs under the road when we were little, and we always wondered, where does this stream go? Where does it come from? And we could never really figure it out because we never walked all the way to where the stream starts. But I'm lucky that in my job I get to look at lots of different streams across the East Coast here in the U.S. So I work for the U.S. Geological Survey, which is the science agency for the Department of the Interior in the nation. USGS has a bunch of different areas that it focuses on. People might be familiar with the USGS from monitoring volcanoes and earthquakes, but USGS also has a big program in water and land resources. So we monitor how much stream is flowing through rivers across the nation, and also we do a lot of mapping looking at what the landscape looks like in terms of land use, how many houses and buildings and roads and farms are in the landscape, and mapping looking at sort of the elevation of the landscape. So today we're going to try to follow the flow here and look at different streams of all shapes and sizes in urban areas. So we're going to start with an urban stream that's just to the west of here called Richland Creek. So we are where that little bubble is, and we're going to go transport ourselves to where that X is. And this is where the stream flows under Wade Avenue. So here's a video of the stream after about an inch of rain. This is Richland Creek right under Wade Avenue. You might not know when you're driving along Wade Avenue that you're actually passing over a lot of streams within the city. But this is what this stream looks like when we get an inch of rain. So you can notice some things about this stream. We see a lot of water flowing through this stream. It's coming out of this culvert. We see two different colors of water that are kind of mixing together. You can see that there's some water that's flowing in from the one side of the stream. So there's water coming out of that culvert, that sort of tunnel there, and then there's also water that's coming in from the side that you can't really see, where it's coming from, but that those two streams actually have different colors that are mixing together in the middle of the picture here. And then there's a light in the tunnel, which is kind of weird. I don't know if you see the light at the end of the tunnel in this video. But we can look at what the stream looks like during low flow conditions. So when it hasn't rained in a while, it looks like that picture on the left. During low flow, so you can see that that tunnel actually has lights in it. I think the city of Raleigh was maybe building a greenway trail that didn't quite connect to anywhere, so you can actually walk through the tunnel, and it has lights in it, which is kind of weird. But then if we look at the stream during high flow conditions, we can see it looks very different. The water's more turbid, it's brown, there's a lot more water flowing through this stream. So the question is, where is all this water coming from? Well, we can actually map the watershed, so the drainage area that's flowing to this stream. So this is the watershed for the entire stream, not just that one little culvert. We can also put our streams on top of that map. So if we zoom into the section where this video was taken, it's where that X is on the map on the right side. And we can see that there's actually two streams that come together here. And on the one side, we have a stream that drains north through PNC Arena and some of the more developed areas and roadway areas. So that's actually the portion of the stream that's coming through this culvert here that looks kind of brown. So that's showing us a lot of roadway runoff the rain that falls on the street and then gets sent into the stream. So it picks up any pollutants that are on the stream, or pollutants that are on the roadway, and sends them into the stream. If we look at the other stream coming in from the, flowing into this picture from the western side, flowing to the west, we can see that that area has some agriculture. So there may be some stream bank erosion or other things that are happening in that other side of the watershed that are contributing a lot of sediment to the stream. So just by looking at the color of the water, we can kind of tell a little bit about where the water is coming from. And it's important because basically all of our roadways and rooftops are often connected right to our stream. So anything that's on the roadway gets right into the stream without any kind of treatment at all. So water that goes in our storm drains ends up in the stream. So anything that's on the road or on our sidewalks or lawns gets sent right into our streams without any kind of treatment. So does anybody know what watershed we're in here at the museum? Any ideas? What did you say? The Neuse? Okay. So we're in the Neuse, and then if we think about like a smaller stream within that larger area, any ideas? What's that? Pigeon House. Yeah, so we're actually in the Pigeon House branch watershed. So that's the name of the smaller stream that drains into Crabtree Creek and then the Neuse River. So where that little X is on this map, we're at the very top of the watershed. So basically, everything that that falls on the roadways here will eventually end up in the stream and travel all the way through the stream network to Crabtree Creek. But you can see on this map here that there are streams that I've mapped here throughout downtown Raleigh. Has anybody seen a stream in downtown Raleigh? Like when you're walking down the street? No, we don't really see them, but they are there. So where are these streams? You can actually find these streams if you look behind parking lots and buildings. So here's just some pictures for reference if you want to walk around after this to look for Pigeon House Branch, the actual stream itself. You can find it not a few blocks away from here, behind a parking lot, or on the at the edge of one of these roads that sort of cut through the watershed. But in a lot of places, we've actually buried these streams into stormwater pipes and culverts. So here's just some pictures of what a buried stream looks like. So you can actually look down through some of the storm drains around the city and find, you can see the stream flowing beneath your feet. So we can actually look at where all those pipes are. So these red lines are where all the stormwater pipes are in the Pigeon House watershed, and then we can overlay that with the streams, and we can see that a lot of these pipes have streams inside of them. So we've paved over the stream so that we can build our buildings on top of in downtown Raleigh, so we can have businesses and houses for where we want to live. We can also look at how much pavement covers the watershed. So there's about 45% of the watershed is covered with pavement, and we can lay those streams on top of our watershed again, and we can see that a lot of that pavement covers those streams. So our streams, rather than looking like a forested, pristine watershed or stream area where there's lots of trees on the banks, instead we have streams that are lined with concrete or buried into pipes. So what happens when we pave a watershed? Why is this important? When we pave our watershed, it changes the balance of our water cycle. So the water cycle kind of explains how, when it rains, that water moves throughout the landscape. So when we get a rain event, that water in a forested system, most of it will infiltrate into the ground and become groundwater, and not a lot of it runs off into streams, but as we add more and more pavement, that leads to less infiltration of that water. When we take out trees, that results in less evapotranspiration, so those trees suck that water out of the ground and put it back into the atmosphere. But when we remove those trees, we lose that piece of the water cycle, and those two components have to balance out with the total amount has to kind of stay the same, so then we get a lot more runoff. So we have less infiltration, less evapotranspiration, and a lot more runoff in our urban streams. And this can lead to flash flooding in cities. This can lead to water pollution when we have all of that water running off our roadways. If we have overflowing trash cans with bags of poop, dog poop, then all of that poop's going to go right into our stream without any sort of treatment. In some cities, there's so much water in these pipes that they actually can surcharge and become little fountains. So all that water that's in that pipe can shoot out of a manhole and become like a little fountain, which is not what we want. So USGS has a network of monitoring sites throughout the city of Raleigh and across the whole country. You can go online at this website and see a map that will let you zoom in and see where USGS is monitoring stream flow across anywhere in the United States. So at each of these stations, we have a stream flow gauge, and there's a little diagram of what a stream flow gauge looks like. Basically, we have a sensor in the stream that measures the depth of the water in the stream channel, and then we have a whole team of hydrologic technicians, these folks who their whole job is to basically go out every day and measure how much water is flowing through all these streams. They go out and measure the actual flow of the water in the stream, and then we can get a relationship between the depth of the water in the stream and the volume of water flowing through the stream over time, and actually get an estimate of stream flow every 15 or 5 minutes. So this information is transmitted over satellites or radio, and it gets uploaded to our website, and you can go online and actually see real time, so in the last hour or so, what the actual stream flow is at all these different stations around Raleigh. And there's about 20 stream flow stations within sort of the Raleigh area where you can get this type of information. So we're going to look at the one on Rocky Branch, which is on NC State's campus. So we can look at the actual stream flow measurements, and there's also a sensor there that measures precipitation. So we know how much water is flowing through the stream, and we also know how much rain fell. So if we look at this record, so the black line there is how much water is flowing through the stream, and the blue line on the top is how much rain we got. So if we look a couple days ago, we can see that we got about 2.2 inches of rain, and the stream actually rose 1 foot in 10 minutes, which is a lot. And then we had another event that happened the next day where we got about 3/4 of an inch of rain, and the stream rose 3 feet, which is like this much, in 20 minutes. So that's pretty quick. So we can use this information to understand how quickly water is moving through our streams. And if we take this information and we look at a lot of different streams, so this is work that I did during my PhD research, where I looked at 72 streams across the nation in 9 different cities and counted how many of these high flow events there were on average in a year for all of these different locations. So each of these points here is one stream where we measure stream flow, and you can see that as you add urban development, so going from rural watersheds to urban watersheds, you have an increase in the number of these high flow events every year. And we can also look at where the streams in Raleigh, it's actually looked at streams in Raleigh, which are these other dots on this map here. We can see Rocky Branch falls towards the top of all of the streams here. So if you look at Rocky Branch, we're in an average of 40 high flow events per year, compared to a stream that was more forested, only had 20 high flow events per year. So twice as many high flow events when we look at an urban watershed compared to a more rural or forested watershed. But you can also see here that there's a lot of variability across all of these different streams. So even at the same amount of development, so if we look at this line here and all of the points that kind of fall around it, you can have anywhere from between, 15 events per year to about 40 events per year, which is a big range. So why are some streams flashier than others, even though they have the same amount of development? Well, we can think about how the landscape itself might influence how quickly water moves through city. So if you have things like lakes and wetlands within your watershed, those things can store water and slow it down and can lead to less high flow events given the same amount of development. You can also have things like topography. So if you think about a really steep watershed versus a flat watershed, a steep watershed is going to move water more quickly. Water moves faster down a steep hill than somewhere flat. So that can also influence how quickly water moves through the landscape and into the stream. Also, not all neighborhoods are created equally, so all of our neighborhoods develop at different times. So this is just kind of showing you some hypothetical development trajectory. So looking at how development happens over time, and if we look at just a neighborhood itself, we can kind of pick out areas that were older development. So if we overlay those impervious surfaces on top of the watershed, we can see that this little section of this neighborhood was built in the 1930s. It has less dense development, but then you can see kind of newer developments that happen through time here in these different little sections of neighborhoods. As different subdivisions are built, we can see that they all kind of have different characteristics. So we started building more neighborhoods with cul-de-sacs and things during the 70s. So this is important because the age of our neighborhood often determines what type of stormwater management practices we have within a watershed. So older areas like downtown Raleigh, basically the way to manage stormwater was to send it right to the stream. So we built all of these pipes that connect the streets right to our streams. But then as we started to realize how that can have negative impacts on the stream and the health of that stream, we started building things like detention and retention ponds to store that water. Rather than sending it right into a stream, it goes into one of these ponds before it's discharged into the stream so that it gets some kind of treatment. And then newer types of watersheds, newer developments are starting to do more like low impact development where we're putting things like bioretention cells, rain gardens, these other types of practices that are smaller and use vegetation and soils to try to infiltrate and clean up that water before it flows into the stream. So what my research is looking at how using a lot of these newer types of stormwater management practices, what is the benefit that those practices have when we put them in urban areas? So we've been monitoring some streams located in Maryland, just a suburb of Washington, D.C., and tracking these watersheds as they go from an agricultural landscape. So this watershed was agricultural in 2004. It had very little pavement, only 2% of the watershed was covered in pavement. And then in 2007, you can see a lot has changed in this watershed. There's 44% of the watershed is covered with pavement or rooftops now. And basically it's a suburban neighborhood. So we have 5 watersheds that we're studying in this area in Clarksburg, Maryland, which is just a suburb of Washington, D.C. We have a forested site where basically the whole watershed is covered by forest, and then we have an urban control site, which is developed with this type of more detention-based stormwater management, so those large ponds that store stormwater, and then we have 3 treatment watersheds where the development has incorporated these newer low-impact development designs using rain gardens and other types of practices to manage all of the pavement and rooftops before it goes into the stream. So you can see the number of these different practices in those 2 of the treatment watersheds that are fully built out now. Each of those dots is a different type of stormwater practice that's meant to clean up the stream. And there's a lot of different types. I don't know if you guys can read that, but there's a lot of different types of stormwater practices on there, things like dry wells, swales. There's still some retention ponds within the watershed, but there's more of these other types of practices. So we've been monitoring these streams, and there's a USGS stream flow gauge at the bottom of each of these watersheds. You can see the circles on there. That's where we measure how much flow is coming through the watershed. So we've taken all of that stream flow information, kind of like I showed you on Rocky Branch there with the stream flow over time, and we've identified each little storm event and the amount of rain associated with that storm event. And then we can look at how much rain it takes to trigger a stream flow response or something detectable within the stream across these different types of watersheds. And that's what this plot is showing you here. This is looking at how much rain it takes to initiate flow. So on the x-axis on the bottom there, you have the amount of precipitation. And then on the y-axis, we have the probability of a stream flow event. So we're going to look at a 75% probability of having a stream flow event on the y. And then if you go down to the x-axis and look at how much rain it took to trigger that flow response, we can see that in the urban watershed, it only takes 5 millimeters of rain to have a detectable response in the stream. Whereas in the forested watershed, it takes a lot more rain to trigger that same response. It takes about 17 millimeters of rain to trigger a response, which means that for those smaller sized events, all of that water is infiltrating into the ground. The forest is able to absorb all that water, whereas in the urban watershed, that water just runs right off for those smaller events. And then we can look at our treatment watershed before it was developed. So that first picture that you saw when it looked like an agricultural area, it was pretty similar to the forested site where it took a larger amount of rain to trigger a flow response. And then we can look after development, how much rain does it take? So these treatment watersheds are kind of in between the forested and the urban control site, where they're not as able to store as much water as the forested site, but they're not as flashy as the urban site. So this would indicate that those stormwater practices are having some kind of benefit in terms of the flashiness of the stream. We also can look at the amount of peak flow, so what is the peak of that event and the total amount of runoff. So we looked at this watershed again, and we can see that given like a similar amount of rain before development, we don't have a big response in the stream. So the amount of rain that's falling through the stream is less than after development. And if we have a rainfall event that occurs when we don't have rain in the previous 3 or 4 days, we actually see that the peak of that event is much lower than if we have a rainfall event back to back, which is the dark blue line there. So this would indicate that those stormwater practices are able to store some of that water and reduce the peak flow within the stream. We can also look at a bunch of different events over time across a range of precipitation amounts, and we see that even though these practices are meant to store all of the water within the watershed to prevent all this runoff from going into the stream, we do see an increase in the amount of water within the stream, so the volume of water, the peak flow, the peak volume of that water going into the stream for a certain event, and sort of the proportion of the water that's sent to the stream. So even though we put all of these practices in this watershed, we're not able to store all of the rain that falls on the watershed. We can also look at water quality. So here's some information about those watersheds that the county has collected, and looking at how specific conductance, which kind of you can think of as like the saltiness of the stream over time. And we can see that the saltiness of the stream is increasing in all of these watersheds over time, but more so in the treatment watersheds that went from that agricultural landscape to an urban, suburban development. So where our streams are becoming saltier because we're adding all of these roadways that connect the landscape right to the stream. Even though we have all of these stormwater practices, there's still these connections to the stream. And they're not designed to treat things like salt, so that salt is still getting into our streams. We can also look at how urban development changes topography. So here's what the watershed looks like before development. You can see these sort of valleys and stream network, the valleys that form the stream network within the watershed. But then when we develop that watershed, we flatten out the landscape so that we can put houses and roads. So you can look at the difference between these two images showing how much the topography has changed over time as we build out this watershed. And we can look at areas that were filled in or excavated within the watershed. And we can find areas where streams and springs were buried, so valleys that were filled in so that roadways could be built within our watershed. So almost a meter of earth was moved for every meter of watershed area in this watershed during development. So huge amounts of soil were moved around when the watershed was developed. We can also look at the health of the stream itself. So this is showing you the benthic integrity score. So this is the bugs that live in the stream, and they're an indicator of how healthy the stream is. So in our forested stream, we can see that the stream is pretty healthy. The scores are in the good to excellent range, whereas in the urban control site, the scores are fairly poor. And then we can look at those treatment watersheds over time and see how the health of the stream in terms of the benthic community or the bugs that live in the stream has changed. And we can see that in the treatment 1 watershed, there was some decline in health during the construction phase of development, but then the stream was able to sort of rebound and come back to a better condition, or a condition close to what it was before development. But then in the treatment 2 watershed, we see that during construction, the health of the stream declined and has kind of continued to decline after development. We can also look at how healthy streams are in Raleigh. So the city of Raleigh actually monitors the health of streams at multiple sites across the city. So each of these little diamonds shows you a location where the city monitors the same sort of information, the benthic macroinvertebrate community within the stream. And we can look at how all these different streams plot out across the streams that they sample. And we can see that a lot of the dots here, so any dot that's higher on the plot here means that the health is poor or fair, and then good scores are lower scores, which is kind of counterintuitive, but basically half of the streams are in poor to fair health, and the other half are in this good to excellent condition. So we can look at those two streams that we talked about today, Rocky Branch and Pigeon House. These are both fall in the fair category of stream health when you look at the actual bugs that live in the stream itself. Another thing that we look at with the U.S. Geological Survey is the contaminants in the water. So urban streams often have a lot of contaminants in the waterway and waters as well. So a large regional stream quality assessment was done a couple years ago in cities across the Piedmont of the Southeast. So looking from Washington, D.C., Raleigh, down to Atlanta. Folks went out and measured all of these different streams and looked at the contaminants in the water. So I'm showing you here, this is a heat map showing a bunch of different pharmaceuticals that were found in the water. So a darker color means that there were more pharmaceuticals detected in the stream. So it's not telling you how much of that pharmaceutical is found in the water, it's just telling you that it was there. So kind of presence or absence of pharmaceuticals in the water. And we can look at what types of pharmaceuticals are found most often in these streams, and you can see that these are 3 common pharmaceuticals that were found in these streams. And we can also see that 2 of these streams, and these are all streams in North Carolina, have a lot of different types of pharmaceuticals that are found in these streams. And if we look at those 3 streams, what do they have in common? Does anyone have any ideas of what might be in common? Like, where do pharmaceuticals come from? These aren't things you would normally find. Wastewater treatment plants. Yeah, so all 3 of these streams have a wastewater treatment plant. So any pharmaceutical that we consume that our body doesn't use, comes out in our urine, and then it goes to the wastewater treatment plant. Wastewater treatment plants aren't designed to remove pharmaceuticals from the water. So all of that's going to end up going right into our streams. So this is an indication that over time, if we don't come up with technologies to remove those pharmaceuticals from the water, it might become more of a problem in the future. This isn't saying that those pharmaceuticals are at, very high levels in the stream. They're actually very low concentrations, but we're actually able to detect them across all of these streams. Every stream that was monitored, even some of the more rural ones, had some kind of contaminant identified in it, which is a big problem. So what I've been working on more recently is looking at some really small headwater streams across Raleigh. So last month we sampled 19 streams within Wake County. These little polygons here show you the places that we sampled the stream. So we sampled sites that have a range in the type of sewer infrastructure within that watershed. So we sampled watersheds that have a high density of septic systems. We sampled watersheds that have a high density of sewers that are newer development. So in theory, these sites would have fewer leaks and breaks. And then sites in downtown Raleigh that are older development, a lot of sewers where you might expect there to be more leakage from pipes into the stream itself. So at each of these places, we go out and we collect a water sample, and we send it to the lab to look at things like nutrients and ions in the water. And we also can use sensors. So here's a picture of two types of sensors that we use to actually measure instantly what the nutrient concentration of that water is. So we look at nitrate and the saltiness of that water. We can look at specific inductance of the water and get like a real-time measurement of that, and also things like pH and dissolved oxygen in the water and the turbidity of the water. So how basically the clarity of the water. So we're going to use this information to try to do a little detective work to try to identify what kinds of water quality stressors are leading to some poor water quality in these small urban headwater streams across Raleigh. To kind of supplement some data that City of Raleigh has collected, we kind of nested our sites within sites that they sample for water quality. So that's the kind of new, fun, exciting stuff that I've been doing recently, looking at urban streams around Raleigh. Just to leave you with some concluding thoughts here, what did we learn today? Well, we need to recognize that urban streams can be assets. You know, these are things that people can value and enjoy if the water is not of poor quality, but these streams have a lot of issues. So because we put so much pavement on the landscape, that alters the water cycle and how water moves through the watershed. And that can lead to degrading the water quality, so the quality of that water, and also the quality of the things that live in that stream, so the benthic communities and the fish communities. But we also found that not all development is the same, and that the plumbing, how we sort of plumb our watersheds, really matters. So we can think about that when we're walking down the street, you know, and you see these storm drains. Maybe think about where those end up. They don't just disappear into some black hole. They actually connect to a stream or some kind of stormwater practice. So we don't want to just dump things in storm drains, because eventually it's going to end up in these streams, and these streams, a lot of these streams might end up as drinking water for somebody else. So all of these streams drain to somewhere where someone might get their drinking water. So here, you know, we get our drinking water from Falls Lake, but there's a lot of streams like from Durham that drain into Falls Lake. So we need to think about how we build our cities and manage our water to try to make urban areas more sustainable in terms of water quality and quantity. So that's all I have. I hope you guys learned something about urban streams, and maybe, you know, you go around and look at where these streams might be within the city of Raleigh. I'm happy to talk to folks afterwards or take questions. So thank you.
Let's give her a round of applause. Thank you very much.
You can also follow me on Twitter. I'm always tweeting pictures of urban streams. So if that's your thing, you can follow me on Twitter and learn more and kind of keep up with what I'm doing.
Sounds good. We've got time for questions if you want to take a few questions. If you've got one, wave at me. If you're here on the first floor, I'll bring you a microphone so that anyone and everyone can hear. If you're on the second or third floors and you have a question for Krissy, wave down at us, and then we'll call on you and you can yell at us, and we'll use the microphones to repeat your question just to make sure that everyone can hear. So if you've got one and want to get us started, I see your hand. Thank you.
Okay, I have a question. So on your slide about the different studies in Maryland, you talked about the different best management practices, stormwater control measures. One of them was dry well. What is a dry well? I've never heard that before.
Yeah, so a dry well is actually connected to a downspout. So each of these houses, their downspout is actually connected to this storage container that's buried underground that allows that water that falls on the rooftop to infiltrate into the ground or be stored in this like tank underground. So it's a way to manage rooftop runoff from your downspouts. Rather than just like sending it into the street or into your lawn, it actually puts it into this container that allows that water to slowly like infiltrate into the ground. Right, yeah. And it has holes in it, so it slowly leaks out. Yeah.
Others wave at me. Do you know, is there a way of doing development or building homes and apartment complexes in cities that doesn't have these kinds of impacts?
Yeah, so this is a hard problem, right? So, when we develop an area, it takes a lot of space to put these stormwater practices. So something like a retention pond or detention pond takes up a lot of space, and developers want to make a return on their investment in terms of development. So it's kind of this trade-off between being able to build houses and manage that water and how much space we allocate towards these types of practices. We also can't manage a 4-inch rain event. Like, there's no way that we can store all of that water on our landscape unless we build huge storage ponds. So there's kind of these trade-offs in how much water we can actually store within our neighborhoods versus send into a stream. If we have something like a hurricane, we can't really design something to mitigate that amount of water. But some places are kind of turning park areas into these areas where the stream is allowed to kind of expand into this. The stream is surrounded by a floodplain, which means that area floods frequently. So if we build in the storage along our river networks, we can actually, instead of building houses or things like that near our stream, we can kind of manage some of those bigger events. But yeah, it's a hard problem. Engineers are trying to do what they can, but we have to kind of keep adapting and trying new things.
We got a question from the web. Dave wants to know, can cities require developers to use some of the new methods of mitigating runoff? If they can and has it had a positive impact on the quality of water flowing into streams?
Yeah, so a lot of places have requirements for development to have to manage a certain sized rain event. So typically it's about an inch of rain, where developers have to put enough practices in the development to be able to store a 1-inch rainfall event. So that's going to have positive benefits, but if you have a rain event that's bigger than that, then all that water won't be able to be stored, and it's going to go right into, these practices will overflow into the stream. So some places, are thinking about, well, what should that number be? Should it be an inch of rain? Should it be 2 inches of rain? And with, changing precipitation patterns into the future, we're having more and more intense rain events. So we really need to think about what those sort of design criteria are for our new development and redevelopment areas. So maybe that answers the question. I don't know.
I mean, is part of the answer just that everybody has to get rain barrels from here on out?
I guess it's voluntary, right? So you can do what you can to manage stormwater from your yard. City of Raleigh has a rainwater rewards program, so people can go and the city will actually pay a certain percentage of that, the cost of that practice to put in something like a rain barrel, or well, they do cisterns, but a larger rain barrel and rain garden. So they'll actually pay 75 to 90% of the cost of that practice. They'll reimburse you the cost of that. So you only have to pay 10% of the cost of putting in something like rain garden, depending on where you live. So everybody could do, their own small part to manage stormwater, but it takes a lot of effort to get people interested and willing to spend their own money to sort of deal with this problem. But everybody pays a stormwater fee. So your stormwater fee is going towards programs that the city actually puts in these different types of practices in certain areas to try to reduce the quality of the water. But it's been really hard to find concrete sort of studies that are able to document the water quality changes associated with an individual practice. You really need a lot of practices to make a change at a watershed scale. So you could look at one little rain garden and how much water it's storing, but if you want to know how many of those it takes for the stream to improve the health of the stream, it's not just about the quantity of water. There's also a lot of other stressors that could be impacting the stream. Things like temperature. So if we remove all of the trees around the stream, then our stream's going to become warmer. So if we plant trees around the stream and have a buffer area that shades the stream, then that can help reduce the temperature within a stream.
All right. Any other questions? Wave at me if you've got one. If not, maybe you can hang out for a couple minutes if folks want to say hi, meet you in person.
Yeah.
And I'll say thanks for coming to the Lunchtime Discovery Series this week. We'll be back here next Wednesday at noon with actually the museum's Chief of Research and Collections, Jason Cryan. He's going to be talking about what he says are the coolest animals on Earth, hoppers, little insect creatures. But he gives a great presentation. You will learn something you did not know before. So make sure you're here next Wednesday. Tune in online, and we'll see you again soon. Have a great day, everybody.
Thank you.